Good morning, everyone. How are you doing this morning? I think we'll go ahead and get started here. Looks like Frank is having a little bit of trouble getting the recording to go. Now it's working, so we'll go ahead and get started. So this class today is going to be a little bit different than the previous ones. It's be a little bit less about the individual modules that we work with in GridLab and more sharing our experiences with how we've used GridLab to create basic power flow models that are equivalent to those that are in, say, SIME, Synergy, Windmill, or other more standard formats, and then how we go the next step beyond that and populate those with time series types of loads and load shapes that are what we find to be representative of the different areas that we're looking at. And so what I kind of want to be a little clear about, this is a couple ways that we have come up with to approach this problem. So just kind of sharing our experience. I know of at least maybe a half dozen others out there that have similar or even different ways of doing this exact same thing. Where I know it's not violating any trust or anything like that, I'll try to share some of those experiences. But for the most part, just realize that there are other ways to do this. This just happens to be the ways that we have worked with it and have had success with. And of course, with different data sets and different data points and different information, you can always come up with new and or better ways to do this. So with that, we'll go ahead and start on the actual presentation here. So really what the whole basic process is kind of a three-step process. So we're really taking the basic models that are built into, say, SimDist or Synergy or any of these other type of tools, and converting them from that database structure. We use the Access database inputs and convert that into a GLM so that we have a base power flow model. We do this with a Perl script. I'll show you that script here when I kind of walk through this presentation. I'll show you the script that we use and for walking through there. And really what the whole idea of this first step is to just convert the power flow and validate the model. That's the whole first step, is just to make sure that you get that initial conversion taken care of correctly. Obviously you want your voltages to match across the entire system where you can, P's, Q's, currents, however you want to measure that. Usually we do kind of a spot check on there. Really what this does is just moves that model into the GLM language and gives a GridLAB-D equivalent of the model that we can look at and say, yes, it's validated, we get the same power flow answers. So it's a very base thing to start from. So the next step of that is we want to actually convert those static load shapes into, or static loads, into some kind of load shape. Now there's a whole series of things you could do there. You could start all the way from very basic load shapes, 24-hour load shapes, or you could go all the way to the area that we've gone, which is converting those into representative house models with end-use loads attached to them, water heaters, HVAC systems, lighting, all that type of thing. And all that depends on what type of study you're trying to do. If you're looking at a very basic, say, reliability study, for example, you probably wouldn't want to go to the pain of trying to convert those all to house models and trying to calibrate that to data that you have. Probably much easier to just convert that to a load shape and place that at each of the locations. So what we're going to go through today is how we do that last one, the most, what I'll call the most complex version of that. And we'll walk through the MATLAB scripts that we put together, and I'll talk a little bit about some Python scripts that we're creating that match up with that, so that you don't have to have MATLAB to do that anymore. And then the final portion of it is then what you really care about is really you want to look at new technologies and how they're going to affect what you're basically what you're trying to look at, and you can look at your different metrics and things like that. And of course, once you do that, your scripting is basically there to make sure that when you go from your base model to your new technology model, nothing changes except the things you want to look at. So you don't get some random errors that are floating in there that make some kind of differences. And again, we do this with the same MATLAB script, and we'll talk about this a little bit when we get into some of the details here in a few minutes. but I want to kind of go over some of the high-level overview at first. And I apologize, I'm just getting over a head cold here, so if I have to step out for a second every once in a while, it's because I'm probably coughing. So here's just kind of a flow chart of the basic process. Kind of gives a little bit of a visual breakdown of it. But really, what we're talking about is we have the basic. We're converting the model to GLM via this Perl script. Then we're running it, and of course, we want to see does the power flow solution converge. And the answer is not always. And I'll go into in a few seconds. I'll go into a few reasons why that happens. But we actually want to go through and identify some of these errors. We rerun it. We end up getting eventually we get a convergence, and then of course we want to actually update the conversion script, especially if you're going to be doing this more than once. We want to make sure that we actually loop this all the way around so that eventually this portion right here, does power flow converge, becomes a very easy and static and always works type of thing. And the reason I bring this up is because every utility's database is slightly different. We'll have different places where they put different, different fields where they'll put different information. Some fields will populate. Some of those will make it to the. They'll populate like switch open, for example, and a switch may be populated in 4 or 5 different places in database, but actually only one is used, so that's the only place that it actually gets populated. So it's kind of important to make sure that we get through that first step to make sure that we're getting all the right information transferred across. And so then once we've been able to actually get a power flow solution convergence, then of course we want to actually match up the voltages and real and reactive power. Typically we only look at real and reactive power at the substation to match, but we'll look at voltage across the entire system. And of course we're rerunning that model until we actually are happy with it, and then we move on to the next steps, which we'll talk about here in a second. So just because I'm not super familiar with Perl myself, we've had other people who wrote these. I actually wrote some directions in here about how to actually install it, use it, all those different types of things. But again, let's go over a little bit more of the high-level pieces of it. Right now, like I said, we use this for Simon Synergy. We provide both these scripts that we have available. As far as I can tell, they work across multiple versions of both these tools. But these could easily, adapt it to other formats, say, for example, Windmill or OpenDSS or anything like that. The second part that this script actually does is we place what I'll call classification tags throughout the GLM file. This is for the loads, so that we have an understanding of what type of loads these should be. I'll go into that a little bit more detail. This occurs in the Perl script to make sure that as we are posting that information in there, we'll actually have that information for a later script. And then, like I said, it does some very initial checkings. It actually calls out GridLAB if it can find it. We'll actually run the model and does some very, very, very simple initial checks, things like islands or zero length lines, things like that that GridLAB-D doesn't handle on its own. And of course, there's always the question, why Perl? Basically because it's free and it's a very good scripting language for text processing, things like that. Like I said, here's some directions on, I'm not going to go through this in person here, but here's some directions for anybody who's not used Perl before. It's a fairly standard language that is fairly easy to read. I'm not sure how easy it is to use, but at least when I'm looking at it from someone else's code, I can read it and modify it. One note here is that this only works on 32-bit Windows. We haven't done any type of 64-bit Windows type of modifications to it, and it certainly won't work in Linux because it calls ODBC and Excel parser. So this is a Windows-only application at this point. And then there's a couple of packages that you have to install to make it work with it. And again, this goes through all the directions on how to do that. And then just to basically how you would run this is when you look at the the outputs from your database conversion from, say, SIME or Synergy. You'll get two files. One is usually like an equipment database, and the other is the network itself. You can see they're both in database format. You just load that into your script and call it, and then basically it'll create a new GLM with this name. One thing to note on there is you can sometimes run into some ODBC permission problems to make sure, especially if you're on a work computer, that working folder must have read-write access. So if you have any problems with that, make sure and run it over with your network administrator. I'm sorry, this is a little in the weeds at this point, but we'll get back to the kind of high-level stuff here in a second. Okay, so the point is, what are we actually trying to get out of this? So again, we get this new GLM that is basically a file called whatever you named it .glm, and this really contains all of the power flow information down to typically down to the primary side of the residential transformers. This is true because most of the commercial solvers at this point don't support past the primary side of the transformer down to the they don't support down to the 120 240 volt system. My understanding, especially I know Windmill now supports that level of detail, and my understanding of some of the other commercial vendors are starting to support that also. But at the time we created this a couple of years ago, that wasn't true. So Tony, so if you're using just the single right now, then it will not work with the script as we have written it. So it's basically that's the way that we have created it, and you would have to kind of modify the script to work with that. That said, I'm going to warn everybody that if you try to use this with any utilities basic output from a SIME or Synergy database, you're going to have to make modifications to the script. We have not gotten to one utility yet, and this is probably I think we're on about our 5th or 6th one right now, and every single time we've had to modify it because the database is slightly different. Good example there is what Tony mentioned is that it's only got one database file instead of two. There's so much customization in these that unfortunately that's the case. We haven't come across a circumstance yet where we could just pick it up and it worked. So sorry to tell you that, but it's going to require some modifications on there. So really what you end up getting is mainly the primary information. So you get the primary side of things, typically down to the primary side of the secondary transformer. Some of the databases do have the secondary transformer information, and if that's so, it will extract it and use it. And then, like I said, we also get this classification of loads, which I'll call residential 1 through 6, commercial 1 through 2, and industrial for now. And we'll come back to that in a minute. But really, all you have is now a base power flow model. Nothing special about it. It's just something that you can use to validate your conversion at this point. So there's a few things that kind of go on under the hood here, especially in a lot of the older models. Anything that was put together any more than about 5 years ago are still typically using sequence components. So what we do on there is we have kind of a common database of cable types, and we try to convert the sequence components to the closest fit for those cable types to try to move it back into an unbalanced representation. The distributed loads are converted to spot loads. So GridLAB doesn't naturally support distributed loads. So what it'll do is it'll try to actually, it basically uses Bill Kirsting's method of putting one half the load 2/3 down the line and the other half of the load all the way down the end of the line. Breaks it into two spot loads. Anywhere that there is industrial or large commercial transformer that are in the database, then we'll use that. But if it's not in the database, then we'll use it. We'll create it from a standard sizing database. So just I think we have a subsection of one of Cooper's databases or something like that we pull from standard sizing of transformers, standard losses, and that type of thing, and put those in there. At the time that we created this, we really weren't using sectionalizers and reclosers, so we converted them all to switches. So right now we don't actually support, we don't actually convert those sectionalizers and reclosers over. We just put them in kind of as a rudimentary switch. And like I said, it does a very simple check for islands and other types of that's kind of bad language there. Basically, it looks for islands and other types of like open switches and floating nodes and things like that. So Frank made a good side note there, is we do actually have sectionalized and reclosers. We just didn't include them in the script right now. So that's a simple modification that can be made to the script to pull those out if you wanted to keep that information in there. As far as the way that GridLAB-D looks at sectionalized and reclosers, they really are just switches with some advanced algorithms, some more advanced algorithms on top of them. So, of course, now we've gotten this conversion. We've got, basically a single power flow solution. Offline, we check that solution against the solutions that are provided in the commercial tool. And like I said, usually we do, spot check a couple voltage levels and power at the substation. There's a little side note here about the reasonable accuracy of these models. At some point, you will find that there are some models that convert well and some that do not. There are some oddities, especially if you're using let's say I'll just pick one out of the air here, like a synergy model that is still using sequence components. Then it's going to be really difficult to match up your answer. So you have to kind of draw the line and say, well, what's good enough? And is representative enough for that planning model to represent what you need on your system. Usually we try to look at something, we try to draw a line ahead of time and go something like, maybe we're within 5%. Usually we shoot for something more like 1 to 2% in that range. But we've had some models where we've had to settle for 5%. And here's some of the common conversion errors that we've actually, or I should say, issues that we've run into. Most of these tools are very happy to use what they call like connectors or zero length lines or zero impedance lines. We don't accept any of those in GridLab. You have to actually explicitly define the physical components in the model. So if there's ever a case where there are, say, a zero length line, then it basically merges those two nodes together and collapses and gets rid of that zero length line. When there's a zero impedance line, it actually throws an error and gets a little unhappy. And so you would have to go back in and probably modify it to either to be, actually have an impedance on that line or get rid of that line and connect it in a different way. So we have a number of different control strategies for capacitors and regulators. Those are not always well defined or have slightly different definitions in the tools. So we've run into a couple cases where we've had to kind of add a few tweaks to make sure that we're capturing the control strategies correctly. I put a note in here that some packages have what I'll call creative power flow solutions. That's not trying to be derogatory or anything like that. It's really actually what they've needed to do to basically it's what they've needed to do to solve their problems. So, for example, you can have kind of like you may have a radial system that has maybe a transformer that is center tapped and branches off and actually comes back in later in the circuit. So topologically, it's actually not radial; it has a slight loop. But most of the solvers are not set up to handle those directly. They may do something like break up the loop and do a slightly different solution in that area. That leads to some slightly different answers than by doing it with, say, the full Newton-Raphson method. So you get a little slightly different answers. In one case, we actually had answers that were off by about 6 or 7 volts between the two different cases because of the way that solver was solving those pieces versus the way ours was. So something just to be aware of. I put this note here of nominal or flat start voltages are not always indicative of the final voltage level. Basically, you'll see in a lot of these models, this is also true in GridLAB-D. The nominal or flat start voltage has basically no bearing on what the final voltage would be, because the final voltage solution is driven by what the voltage is at the swing node. So I've seen a number of cases, ourselves included, where every single node in the system gets a nominal voltage of 7,200 volts, but then by the time you make the solution, the node is actually solving at 240 volts. Something just to be aware of, that when you start to look at those, that's a little mistake that pops up every once in a while. I call these the next one the odd loops that may need to be fixed manually. So a lot of times in planning models, they'll include a switch that seems to go off to nowhere, but really that switch is going off to the next feeder, so that when they're doing reconfiguration or any type of load rebalancing or anything like that, they can attach to the feeder next door. But from the point of view of a power flow solver, that node that's sitting on the other side of the switch looks like an islanded node because the switch is open. So you may need to go back and do some things manually on the side, just actually close that switch or get rid of the node in the switch and things like that, so you don't have any islands sitting in the system. And then the big one, missing data. This is very common. The most utilities are actually doing a really good job in the past few years of updating their planning models and moving some of this data that normally wasn't captured into the planning models. But there is almost always still some missing data. A big one is triplex cabling as a great example, because these planning models typically didn't capture that information. That information is not in the planning model, obviously. So, so there's a lot of moving that information from external databases, or from, even in some cases, from talking with the utility engineers. What's your common triplex cabling size, or what's your common transformer sizing? Do you oversize the transformers or undersize them? So that information is not always directly available, so it may have to be coming from external sources. So we'll come back to hit a few more of these in a few minutes, but we'll go on to the next one, which is really kind of the big portion of this. It's actually populating the feeders. So really the whole goal of this is to replace the static power flow loads with loads that are dependent on time, voltage, weather, markets, other control signals, all these other technologies that we might want to add on here to modify how this load behaves. And then ideally what we want to do is calibrate these time series models to available data. And here I've noted SCADA data. Typically, in fact, in the past, the only way that we've done this is we've taken SCADA from the substation or from the feeder head and matched it kind of at the gross scale. So as a time series solution, we can look at it and say, okay, here's our simulation, here's the data coming from the substation over the course of 365 days of the year, minus a few holidays and things like that. We can match these up within, say, 3 to 5% of time series load behavior. Now, that said, again, we have not had access to things like AMI data, so we've never been able to drill down to that level to really try to calibrate it in that manner. We're really doing this at the gross level to say, okay, we want the entire feeder circuit to look like our modeled feeder circuit. So we haven't really actually drilled down to the level to say, okay, how are we doing on a particular branch or on a particular transformer? We're really only evaluating this from the substation level. So the way that we do this, so the first portion is typically a little bit of a manual process. We really want to classify these loads. So one way we've done this in the past is, for example, with the taxonomy feeders, we actually extracted that information from the databases because it was already available. So they had things like, residential versus commercial, industrial, agricultural. And where we didn't, we actually contacted the utilities and worked with them and were able to pull that information. In other cases, we've actually been able to use aerial photography, say Google Earth is the most common one, So I believe both SIME and Synergy have tools that allow you to overlay the feeder models into Google Earth. And we've done things like looking at the aerial photography to kind of give a rough approximation on size of houses, construction date and types, how many occupants we think live there and things like that, in a very, very gross level. So we might draw a circle around an entire neighborhood and say, well, this looks like 1960s brick-built homes, and kind of leave it like that. We don't really dig in and look at people's driveways and see how many cars they have parked in their driveways. One, that takes I feel bad about that, and two, it takes way too much time. So really, we're doing this at kind of the gross level, trying to look at maybe a cul-de-sac to say, okay, these are all kind of brand new homes, so we'll make some approximations of what this load might look like. And then, of course, and then the next step is that these loads are going to be varying profiles based on where you are. So what happens in South Carolina is far different than what happens in Oregon, and that's driven a lot by weather and sunlight and, of course, different types of construction techniques and things like that. So I'll go a little into how we kind of extract that information here. But really the whole goal here, this first step, is just to say, is to break your loads into some kind of classification bins and then mark them. When we do this with, say, like Google Earth and SIME, we'll actually go into SIME and we'll highlight a region that, say, is like 50 homes, and we'll flag it with a residential 1 flag, for example. I'll talk about that in a second. And that becomes part of the database that's going into the Perl script, and that information gets transferred into this GLM that we've created that's a base power flow model, but we then use that information to populate it with the right type of house here in a moment. So I'll give you one example of the way that we've classified loads. Again, this was a SIME study that we did, and this was, I can actually say that this was in the Columbus, Ohio area. So we actually went through with working with the engineers there and identified kind of a big, broad kind of a category of types of buildings that were in these feeders. And we broke them down into basically 6 different types of residential homes, and these are all like older, newer. We did the breakdown in 1980, less than 2,000 square feet or greater than 2,000 square feet. So basically, older, large, older, small, newer, large, newer, small. So very broad categories of what these loads might look like. And then residential 5 here was mobile homes. Residential 6 was multifamily apartments. And then we broke the commercial into small and large commercial, and our breakpoint was 35 kVA. And then, of course, industrial loads. So that was the particular classification that we used for this study, and in a moment here I'll show you a second way we did this. But I'll talk a little bit more about what these all meant for us. So what we did is we ended up using these residentials or these classifications to decide how we were going to populate the feeder with different loads. So really the whole goal is to take that spot load and to create a series of house models or other things, other load shapes that we're going to try to represent what this looked like. The key being is that this 20 kVA came from a peak planning study, which really was a way of distributing the load in some kind of even fashion on the peakiest day of the year. So say this feeder model had a peak of 10 MVA, then once you hit your load allocation study, you distribute that out by looking at the things like number of meters at a location and things like that, and try to break it down into some kind of fair way. So for example, this node right here may have gotten a 20 kVA listing upon there. Sometimes you have information about how many buildings that might be. Sometimes you don't. So what we've done is we've created what we call a kind of a calibration variable that we call house MVA and com MVA. So that's house or basically residential or commercial. And really what it's trying to do is represent what the average of the maximum load at that location would look like. And that's kind of, it's kind of a little odd thing, but really what you don't want to look at is the individual house. So an individual house may have a maximum of 10 kVA on its own, but really over the course of, say, like an hour, its maximum is probably, its average maximum is more like, say, like 4 or 5 kVA on a, say, really hot summer day. So what we're trying to say is that this is roughly represents what the average maximum load is at that location. But it gives us a little bit of room for calibration. I'll show you how that works here. So we have this 20 kVA load sitting at the end of this feeder, wherever it might be. We're going to assign a value of house VA equal to 10,000. And so that 20 kVA is then divided by 10 kVA, and so we end up getting 2 houses at that location. So we would go through and we would simulate this feeder. We take a look at the peak load on there, and we could say, well, okay, that was it wasn't even close to the substation peak load. We were off by, let's just say, 40%. So we decide that we want to move this house VA to something that would make more houses on this model. And we'd say, okay, now we're going to change house VA to 5,000. Gives us 2 more houses at this location, and it would effectively double the load on the entire feeder because you're not just doubling it right here, you're doubling it everywhere. Of course, this is a pretty extreme example. Usually we're moving that from, like, say, 10,000 to 9,500 or 10,000 to 11,000. But this kind of gives you the idea. Really what this, as you see in the scripts here that I'll show you in a few minutes, this house VA becomes our kind of, I call it the gross knob. It's the big giant knob that lets us swing the load on the feeder, as much as 50, 60, 70% to try to get you kind of that gross calibration to say, well, here's how much load we think is on this feeder. And this is where we try to match up basically the maximum load, whether it actually lines up with the substation's timing of the load at this point is questionable. But we're trying to, in a very gross sense, match the peak load at this point, just by using these variables. So this is what we would use on, say, like on the residential homes and on the small commercial buildings. Note that there's a couple additions that go along with this. Again, this is all how we do this out of a MATLAB script that I'll show you guys here in a few minutes. Note we added service transformers, this guy right here. We added the triplex cabling. Of course, we added the meter and the house and all the loads that go inside the house. These all would have come out of the MATLAB script. And each time you would do this, depending on what value of house VA you assign, would scale these in a different way to give you slightly different answers. So one little note here about the secondary transformers and the triplex lines. Again, these are not typically available in the standard databases. So we will usually extract that information from a standard sizing database, say something along the lines of, allow increments of 5 kVA until you get up to 25 kVA, and then it's 25 kVA increments and things like that, with some standard losses. Usually at that point we're working with the utility engineers to kind of get a better picture of what type of transformers they typically use, and again also what type of triplex cabling they typically use. So we might find out that their runs are typically on the neighborhood of 10 to 50 feet versus another place might be more like 50 to 100 feet, and use 4-aught cabling instead of 1-aught cabling. So try to get a feel for what the standard practice is, so that when we're populating these models, we can actually try to populate it with utility-specific information. So the second type of load that we talked about in this one was the commercial to and industrial. These are fairly large loads. Fortunately, these become a little bit harder to classify as a general approach than residentials. Residentials, at least from the bulk picture of things, are fairly the same. There's not a lot of differences across the population. Again, from a gross perspective. zero down on a single house, of course, they're quite different. But when you start looking at large commercial buildings and large industrial buildings, each of them has completely different processes. My favorite example is, how do you compare what a barrel extruding plant is compared to a say like a aluminum smelter? So they're just basically so different that it's very hard to represent those in some kind of single global model that will help us out here. So instead of trying to represent them with these kind of ETP or thermal parameter models that we use with the residential homes, we make these much simpler. We'll typically use a load shape or some kind of zip model that has a time series component that looks similar to what is happening on that feeder circuit. Best way to do it would be if you had individual customer meter data, which does actually happen quite a bit with large consumers like that. If not, then what we've done in the past is we've actually taken the time series SCADA data for that feeder, we've scaled it, and then fed that basically back in as the load shape for that load. It's a little bit of a cheat, but it's the best information we can get for that type of thing. So, for example, in this particular case, we were creating loads for commercial to an industrial. We normalized it so that on the peak day, we had a scaled value of 1. Obviously, this is not the peak day that I'm showing here. And then basically multiplied whatever that value at the spot load was against that player, and we've got a load shape that looked like this, scaled up by, say, 100 kVA. So we now had a load shape at that location. And to the best of our ability, assigned a zip fraction to it. That's obviously a pretty difficult one to do. Again, trying to compare two different industrial processes, what that zip component might look like. I'll admit there it's a little bit of a thumb in the air at this point. So when you're done, you may have a load that looks something like this, where on 3 different phases, you're going to get slightly different loads because it was an unbalanced load in the database, where this one is somewhere right around a peak of about 100 kVA. So now when we actually classified these residential loads, R1 through R6, what do we actually do with that? So yes, we populate it with, let's say, 4 homes at this location, but we actually had to assign it values now. So what we do is we go through and we create basically a standardized database that goes with each of these different types of load classifications. So for example, in the older homes versus newer homes, you might draw a conclusion that, of course, the older homes have low UA values and inefficient HVACs. So for example, the roof value for the UA might be between 10 and 24 for older homes and between 20 and 50 for newer homes, indicating that more insulation is going into the attic as the homes get newer. But of course, you can have an older home of 24 or a newer home of 20 that debunk that type of idea. Basically, this would look at like a house that's been retrofitted. And then, of course, and notice these are distributions. These are not single values. And the same with the distribution of, say, square footage. So a larger home could be between 2,000 feet and 3,500 square feet, while a smaller home might be between 500 and 2,000. This is all trying to basically populate these buildings across this feeder from a random distribution that will try to represent what the entire population might look like. But again, any individual home is probably not going to represent any individual home on the feeder itself. Again, if we had more information, like AMI information or more detailed studies. So one case that I know people have been working on is actually accessing things like the county auditor's database to look up, what is the square footage at that actual address? What upgrades have they had on that home? What's the age of the home? And accessing that information to actually better inform the model. That's something we haven't done personally, but that's what I've heard other people doing. So then there's some other things, like, obviously the penetration of HVAC types, whether it's gas versus resistive heat versus heat pumps, versus all these, how much air conditioning exists in this area. Those are all very important things to kind of capture to understand what type of load you have on the system. I usually try to capture this from utility survey data. So if the utility has its own internal appliance survey or any type of customer survey information, we try to incorporate that. If we can decide, what's the penetration of gas versus electric water heaters, even to the point of asking the planning engineers who actually know the area, does a major gas pipeline run right through this feeder? Because we need to know how many of these homes are probably gas heated versus electric heated, so we can make a decision about, how many of these homes on this feeder should have different types of heating or water heating type of information. Where you can't get that level of accuracy, you kind of have to keep going up a level higher, all the way up to the point where sometimes we'll use information from the EIA, which is a government website that provides regional information on penetrations of HVACs and gas water heaters and things like that. So we basically try to extract as much detailed information as we can, digging down to that level. But where we can't, we have to kind of draw the line and back that out to say, let's look at some regional data and draw some conclusions from there. So when these models are created, just like we've talked about in the past ones, is that usually we create a house model which has the HVAC built into it. We'll create the water heater explicitly, and then all the other appliances are just simple zip models. We don't try to go too complex on that, again, because there's just not that much information on them. And really when you're talking about, if you're going to say do a direct load control study, these are really the only two components that you're normally going to be addressing. There's not a lot out there besides maybe pool pumps and things like that, but there's not a lot of, say, direct load control on refrigerators at this point. So we really only represent the models this far. So a little bit more on the secondary system models. Like I said, we have to kind of go for some rules of thumbs when we're trying to populate these center tap transformers or secondary service transformers and triplex lines. So we usually do a lot of rules of thumb. Say, for example, talk to utility engineers and say, yeah, usually we try to plan for, for every customer that's going to be attached here, we go with 5 kVA, or maybe it's 10 kVA, or whatever it might be. We'll try to incorporate that. So we'll see when we get into these scripts later, if you ever start looking through them. This is actually right here, the built-in assumption is that it's about 5 kVA per customer. That may be right or wrong depending on the area you're looking at. I just threw some equations in here because this is a good way to convert. Typically when you have your transformer model, spec guides, they list it all as no and full load losses, so I just throw the conversions to how to get your series and shunt components in there. When we represent our center tap transformers, we actually do not only the series component, but we also list the shunt component because they have a fairly substantial standby loss that occurs in there. This is actually one of the big losses that occurs in the transformers, even at low voltages. So we try to throw that in there. So there's these equations in there, so you have those, have that information. Again, like I said, we're adding the triplex cabling in there also. This is one where we typically work with the engineer on the ground or the lineman even. To that point, we'll actually say, okay, well, what is your typical run length? Okay, then we'll randomize it inside that distribution. We'll look at, say, what's your cabling size. So, for example, in this system that we're looking at, it was all 1/0 for residential and 4/0 for the small commercial industrial. Small industrial, I should say, on that. The big ones were obviously direct connected to the transformers. We didn't actually represent the industrial yards, all their lines and cablings and things like that. And like I said, basically what we're trying to do is we're just trying to incorporate the rules of thumb for that area. And of course, like I said before, we're adding a triplex meter to attach the house to. And at that point, that gives us access to billing functions and things like that. So if we wanted to start looking at how much each of these customers is being charged under, say, different rate plans, we can start to capture that information out of it. So I'm going to go into a second way of that we've done this in the past. This is looking at what we called our Smart Grid Investment Grant. We had a set of representative technologies that we were trying to evaluate what would be the technical benefits of these for the entire United States, if these technologies were deployed across the United States. And so this was things like distribution automation, some demand response, thermal energy storage, renewables, things like that. If we were to deploy this across all the feeders in the U.S., then what type of benefit would the U.S. see? And so we're taking a very, very eagle-eye perspective of this type of thing, but trying to get some very informed answers. So we used our set of prototypical feeders that we think represent a large portion of what some average feeders across the U.S. look like. And those models are available for anybody to use. They're on the SourceForge page that you have access to, and you can download any of those standardized models. The MATLAB script that we'll walk through here in a few minutes are all built around those models to work in conjunction with those models. If you use the SIME or Synergy scripts that I'll show you in a few minutes here, those convert to the same format that is in these taxonomy feeders. They work with our MATLAB script. So that's kind of the key there, is that all these scripts are kind of tied together. There's a series of them, but they're all designed to work with each other in the formats that come out of them. So in this case, we didn't go quite into the breakdown as we did with the individual utility study, again, because we weren't looking at any actual utility or any actual feeder. We were looking at some kind of representative feeders. What we really want to do is look at the regional effects of, say, demand response. The amount of load reduction that you have in Texas on a hot day is far different than what you would have in, say, Seattle. So we wanted to try to capture those kind of regional effects. So we went to basically used EIA, so the Energy Information Agency, and went through and looked and basically were able to divide up these regions into 5 big regions, West Coast, North, Southeast, Southwest, and Northeast. Basically say, okay, these are kind of 5 basic climate regions in the U.S. And then inside of here, here's basically what the average houses and commercial buildings look like. And then we were able to populate these feeders with all these different types. So really all we did is divided this into residential and commercial. So those are only 2 load classifications in there. We were able to break it down a little bit further, so we did actually break them down into residential loads 1 through 6 again. And then we classified the commercial loads a little bit differently. We used what we call strip malls, big box, this is representing something like a Home Depot, and then office buildings are kind of like your 2 or 3 story little cube type of office buildings. I'll go to those a little more in a second here, but in this case, we weren't looking at industrial agricultural areas. We really wanted to focus on the small, light commercial and residential areas. In this case, we weren't matching to SCADA data, so we didn't have to go to that level of detail, but we did want to match the peak load from the peak planning study information that we had. But of course, in this case, we couldn't use any local knowledge, but you could use that information when you were doing, again, working with a specific utility, like is there any major gas infrastructure in that area? So here's just a kind of representation of what the commercial loads look like. So small office buildings are just kind of this zonal model. Same with this big box. Strip malls are exactly what you think, some long and thin kind of shopping center type places. So we broke them down again into, like I said, we're again randomizing this type of information so that we're going to get a cross set of different types of buildings that go onto here. that when you look at it from, again, from the kind of eagle eye perspective, the feeder or the substation looks very much like what you would expect, but trying to match up any of these individual loads to an actual individual load is going to be pretty difficult. In this case, commercial loads are pretty standardized because they actually have building codes that they have to match. You can see there's not a lot of variation on there except in square footage and things like, you know, how efficient of a HVAC did you buy. But otherwise, they're pretty standard. So we use this distribution to describe what all the commercial buildings look like. We describe a number of load shapes that work with the commercial buildings. So, for example, this red line here is the plugs during the weekend. You know, well, over here, this is the lights during the weekday. We describe all these load shapes and populate this model with all these types of loads on there. Residential, there was a quite a bit more breakdown. So from EIA, they basically break these down into some yearly information, and then we equated this to a certain type of building. So basically, this describes how leaky. Oops, excuse me. Sorry. This describes, you know, how leaky the building is. This describes the efficiency of the air conditioner. This is your, you know, basically how much insulation you have. We describe these kind of things in this way. And then at every location inside the feeder, we would draw from a distribution of these different types of homes and populate the feeder with that information. So, for example, in Region 1, which I believe is the Pacific Coast, we have a large abundance of, say, homes in the 70s and 80s. So we have a little bit higher efficiency, but they may have a little bit different, say, HVAC penetration levels. So we can look at here, Region 1, for example. So because we're looking at the Pacific West Coast, there's not a lot of actual air conditioning because you're on the ocean. But you can see you have a lot more pool pumps, for example, because a lot of people like the pools. And then actually a lower penetration of one-story homes. So things like that. So we're able to break this information down in a way that gives us an idea of what each of these regions and what type of homes are in these regions, even down to what's the average square footage of a home. So what does this get you? Again, this gets you this feeder model that is the power flow system plus all the buildings that are going to be attached to it, and it gives you a bunch of individually modeled loads that, when you look at it from the substation level, is very representative of what this might look like. So, for example, here is a roughly about an 8 megawatt peak feeder. The blue line here represents the base case model. You know, again, none of these, every single load inside of here is individually represented, as in, you know, it's a building model or some kind of simplified zip component model. But for the most part, this is all building models. And this is a hot summer day. I think this is a Texas example, if I remember right. But you can see the nice air conditioner peak, and then kind of a fall off as the sun goes down, and so people start, you know, the buildings start cooling themselves back down. But then we might look at something like, say, a time of use case, which I believe what this is, and we can look at how that might affect the way that people consume their load. So you can see there's a little bit of a reduction in the peak period, which this peak happens to be about 2 p.m. So we could start looking at this comparison of side-by-sides. So one thing I always like to note is that, you know, when we're doing these studies, we're always most interested about the differentials. So you know, if we're looking at this base case, we really don't care about the base case so much. We want to know what the difference is between the base case and our new technology case. So the calibration aspect of it, trying to match our load behavior to the observed load behavior, is all about getting it, I'll call it good enough. Is basically we want it to be as representative as we can about what we think the system is doing, and then apply our technologies and really look at the differentials rather than the absolutes on here. So in this case, rather than saying that we could reduce the peak load to 7.8 megawatts, we would say that we could have about a 7 to 8% reduction in peak, because we don't want to overdraw too many conclusions from these absolute values that are being represented by these individual loads. So a little bit what we're going to go over now is some of these scripts that we put together, because I think that kind of clarifies things a little bit more. And we put these out there available for anybody to use. So these are all openly available at this portion of the SourceForge account. So you're welcome to download it. If you just go through taxonomy feeders here, you can actually get the feeder models themselves. And then there's a folder called population script that actually has all these scripts and a bunch of input files and things like that. Sorry, I'm turning down the PowerPoint here for a second. I'm going to bring up some more stuff. So if you downloaded the Module 6 information here, you can see that I put some of these utilities on here for you. So what I'm going to do now is kind of take a couple minutes and walk through some of these scripts. In a very, very high level. We're not going to go into a lot of detail. If you have specific questions, please feel free to ask. But I'm just going to kind of give a high-level overview. So for example, here's the conversion scripts. You can see we have a SIME to GridLAB-D and a Synergy to GridLAB-D. At some point, we're going to hope to rewrite these in not this portion of it, sorry. So these will be available. Anybody can use them. Again, if you're going to work with a different database than we have, I'm going to guarantee that you're going to have to make some new modifications to make those. Notice that these are text files. These are actually Perl scripts, so you'd want to rename these to a .pl. SourceForge just does not like you posting actual Perl scripts out to it, so we rewrote those as text files. All they are is a text file that's actually a Perl script. So for example, if you open this up in Notepad, you can see what the actual text is and things like that. We try to make sure that we keep notes on all the changes that we've made over time. I think we've done pretty good documentation in here. It's not perfect, but at least it gives you an idea of what you might be looking at and help you give you ideas about where to go to change things. Let's see if I have a Perl color code. There we go. So for example, you can look at, what's a good one here? So you can see where it's grabbing the different types of cables. So this is looking in the database to look at underground cables. This is looking at the database to look for overhead conductors. So really what it's doing is doing a lot of things like fetching and grabbing information. By the time you get down to the very end of the script here, really all it's doing is printing out a GLM. So you can see, if you're familiar with the power flow objects, you can see here's object overhead line, saying who it is, what phase it's attached from and to, and length and things like that. So really this is the important part, not to really modify that much, because this is the piece that will produce the text file in a format that these next scripts are looking for. But anything that goes up in here and rearranges this information or grabs it from a different location or makes different assumptions, all of this is perfectly, go for it, change it, modify it. In fact, I guarantee that you will have to at some point. So this would be the first step. We'd actually convert this into a GLM. I'm sorry I don't have any to show you, but I didn't want to, because of agreements, I can't actually use any of the utility GLMs that we've converted in the past. But it may look something very much like what we would see from our prototypical feeders. Let me grab one here just to kind of give you an idea. So it looks something very much like this, where it's just a strict power flow solution. It has your configurations and loads and nodes and meters and all that good stuff. So very simple, just power flow solution at this point. So the next step would be to actually use the population script. So I'm actually going to pull this open in MATLAB right now, so that we can actually run a couple of these and show what it looks like. So, so the actual main piece of this is what we call the, it's called the feeder generator.m. So a lot of these are input files and things like that. You'll notice when I added it into the Module 6 information, I kept it kind of broken up so you can see a little bit more clearly. Here's the .m files that you want to use. There's things like players and schedules and weather information and things so it's a little bit easier to see and broken out a little bit differently there. Let me open up feeder generator here. Maybe. There it goes. So you can see this is a massive script. It's pushing 4,500 lines now. And we've broken it up to be fairly easy to use from using it with the prototypical feeders perspective. I'm not going to claim it's easy to use with anything else. It's more that it was what we needed to do our studies. We were looking at 28 feeders that we had to test, effectively 14 technologies, so 15 different types of simulations. So we made this easy for us to use, so I won't promise that it's easy for others to use outside of the prototypical feeders. That said, with the prototypical feeders, it works quite well. But what you see is you have a number of different technologies that we can try to test. So for example, we go all the way from the base case to some automation. We have some time of use, critical peak pricing, direct load control type things, thermal energy storage, and PHEVs. Frank may be able to speak to that. I'm not sure how much of the PHEV is actually in there. And then we have different kind of like wind, some kind of medium to large scale wind, and some very small solar type of things. Excuse me for just 1 second. Yeah, that's what I thought. I thought it was a placeholder itself. I don't think there's anything in there with the PHEVs at this point. There's plans to kind of add that and flesh it out. Anytime that we are planning to do future studies that use these prototypical feeders, we will be adding it directly into this script rather than trying to start from scratch every single time. So this script will always be expanding to include new things so it can try them out. So one thing to think about is this is actually a great way, if you want an example of how to put together any of these technologies, this is a great place to start from. So let's just run this here real quick. So what we have here is we have this feeder generator, but it also pulls in all these different other aspects. So things like regionalization will say, well, which region do you care about? And of course, what's the time zone there? What's the different types of housing characteristics and things like that? What are my heating and cooling set point breakdowns for each of the different regions? So basically, this becomes a repository of different regional information that we then get pulled into the feeder generator. We also have a user configuration. So for example, for me, what do I want to look at? Maybe I just want to look at a couple of different files that I'm interested in. I don't want to do the whole set of taxonomy feeders. So for example, this is where I have my taxonomy feeders located, but I want to actually output it, let's say, into here. So I can put that information in there. And then what I'll do is actually I'll just hit F5 and run this guy. And hopefully it'll not fail. Yes, it failed on me. It didn't like where I was trying to link it to. Let me make sure I do actually have my feeders at that location. Second here, put this right there. Yep, got my user configuration. There we go. Okay. Now it's running. You can see I'm getting a few warnings. This is just because MATLAB in their infinite wisdom changes their random stream number generator every year or two just to make sure you're upgrading. So it's still working. It's just throwing a lot of warnings saying that it's going to be changing that pretty soon. As you can see, it says I finished one, and you can see I probably wrote this script late in the night, so I was a little, had a little energy left to kind of rage against the world a little bit. But basically what it did is it produced these two cases, and we should now have created two new GLMs. And you can see we add a little appendix to the end of the title. In this case, we're looking at technology 0, which happens to be the base case. So if we take a look at this, so we now have a number of additional things that were not in there before. So we have now a bunch of schedules attached to it. We've set the minimum time step, done things like added a profiler and things like that, activated all the modules that we might use, turned on weather, things like that. We have our standard power flow information, but if we scroll down, actually see we've done things like populate the entire feeder with the number of triplex meters that in this case has a bunch of different billing information. So a uniform billing mode of 12 cents a kilowatt hour, a $10 monthly fee, and things like that. And then we've actually populated this with a house. In this case, it happens to be a single family home, what we called residential 4 from before, and that assigned it a number of different characteristics, which I believe that makes this a small home. With take a look at it here, so COP of 3.3, so that's pretty high efficiency. So this is probably a smaller, newer home. But if we went down and looked at the next one beyond it, see we might get populated with a single family 1, which happens to be looks like probably a smaller home with almost no insulation. So this is almost a cardboard box with quite a bit of leakage in the building itself. So what this did is basically it populated this entire feeder with all this information. We also add a few notes to the bottom to kind of say what were the settings that we used in that one. Do things like add, bill dumps and some other recorders and things like that to gather all the information that we might need. Obviously, these were for very large studies, so we actually captured a whole ton of information. That's very particular to what you might want. The next piece is that then we take this, if we take this script and we decide we want to look at, say, let's take a look at technology 8. Let's do direct load control. So we run it again, hope that it doesn't fail. I kid. So there it goes. It's running through there. It's now taking these and repopulating them in a very similar manner to what we just did. As you can tell, this is not exactly a super fast script. It is text parsing in MATLAB, which is not what MATLAB was designed to do, but it's what I'm familiar with. So it is a little bit slow. If you were to generate all 28 of these feeders out of this, you're probably in the neighborhood of waiting about 5 to 10 minutes to generate that. But what we end up getting is now a second file. So now you see this is that same feeder, R1-1247-1, but now it's with technology 8 attached to it. So if we just do a compare, I'm just going to do a beyond compare comparison here. It's a piece of software that lets me do text comparison. We'll take a look at the differences. So in this case, we're looking at a direct load control case, which requires a market. So you can see we've added some information, things like elasticity schedules, which defines basically how customers respond to the price changes. We've added things like the market module and auctions and players and things like that. When you look at things like the power flow, nothing has changed. Right? It's exactly the same as we expected. When you look at things like get up to the first one here. Let's take a look at, say, we're going to look at a house. For the most part, this house has not changed. In this case, we switched from a standard electromagnetic triplex meter. We switched it over to a new AMI style meter, which has slightly different power consumption. That's why you see that difference there. But when you scroll through, you see that the house still has the exact same floor area. It's still a gas type heating. We did some slight modifications to the cooling and heating set points, but not the base set points. So see it's 71 degrees versus 71 degrees here. And then we did things like added controllers to the responsive loads So we could actually have a change in load shape at given prices. We added a controller to the water heater so that when price got to a certain level, we turned it off. But otherwise, everything is exactly the same. And that's really the key, is because we really want to look at differentials where we say, this is exactly what we're going to change on this model, and we want to know exactly what type of response we get from that. So we can, when we look at these two simulations side by side, we can say this is the changes were not related to the fact that we had a completely different random population. It's the fact that we're just comparing one technology to the next. Excuse me for a second. So really that's the whole goal of what this script is trying to do. I'm going to walk you through a little bit of it just to kind of give you a little feel for the way that it works. Let me introduce you to the other pieces here, technology and taxonomy feeder data. There's a couple other scripts that feed into it. Again, feeder generator is the main one. It's the one that's the workhorse that's doing all the work for it. All these other ones you can kind of think as library files. Regionalization is pulling in information that's related to the different regions that we're looking at. User configuration, just really kind of a thing to make it a little bit simpler for different people. So you can see myself, Frank is in here. For those of you who know who Kevin is, his name is in here. So it's got all of our directories and things like that. Just something to make it a little bit easier once you've got it set up. Technology parameters is really about setting up these use cases. So when we look at the technology to test, this is giving us to say we want direct load control. Well, what does that mean? Well, there's certain things, certain technologies that we're now going to add to this model to populate it. So what this does is activates those flags. So for example, if we look at flag 8, which is direct load control here, we're going to set things like, do we want to use homes? Do we want to use commercial buildings? Do we want to use billing? Do we want to capture emission effects, capacitor outages? All these different things. It really kind of sets a number of flags. I don't really care about the reliability stats when I'm doing a direct load control. Don't really care about voltage when I'm doing a direct load control. Then again, when you scroll up here to say distribution automation, which may be, I can't even remember what this one actually is, it really doesn't care about billing because we're actually only concerned about how that affects our reliability metrics. So this is a series of flags that does a lot of things, tells it what technologies to add to the actual feeder itself. And then if you scroll down, once you get past all these cases, once we set these flags, what do we want to go along with it? So for example, if we're going to use homes, what are our default zip fractions? So in this case, we use a zip fraction of 20% impedance, 40% current, and 40% power. What is our heat dump fraction, something that did. Even set some kind of secondary flags. Do we want to use water heaters, or do we not want to have water heaters, things like that. So really it's kind of setting a bunch of different technology flags that we want to look at. So for example, with the battery storage, how big a battery do we want to use? So that sets all these type of information. Then we look over at what we call the tax feeder data. This is information that's very specific to the feeders that we're looking at. I'm going to skip over the general commercial ones because those have some oddities to it. But if we look at, say, the feeder that we were looking at, R1 1247.1, so basically this is where we see things like, okay, well, what is the nominal voltage on the feeder? What is the feeder rating? So how do we size the transformer at the substation? Because we don't actually have that information. So in this case, we know the peak load study was about 7.2 megawatts. So we upped that by 15% to make sure that we had a well-oversized transformer. Didn't have to worry about it. These are the values that we ended up finding that were correct for this feeder, with the average house size of about 4 kVA. Average commercial was about 20 kVA. For things like our CVR study, our volt var optimization study, where we're looking at how would end-of-line measurements help us. This actually assigns the end-of-line measurements. It's called end-of-line points. In in this one, we actually had capacitor outages that we wanted to look at, so we assigned them here. Assign who has regulators. You can also assign different types of controls. What the voltage regulation should be at. A number of different things like that, different prices, different players, and things like that that we want to go with each of the different feeders. And if you scroll down, you'll see that this goes on for each of the all the other feeders that are in the taxonomy. So that's really all. It's basically feeder-specific information. So if you really got into the guts of this script, now I should note that this script, we are actually, as part of another project, rewriting this in a Python script, which we hope to make available by the end of this summer. The advantage of that is, Python, like Perl, doesn't have licensing issues. It's all open source software and things like that. Tony, Frank will post a link here for you for the SourceForge page, or if you downloaded the Module 6 files. So here in Module 6, there's feeder population. We've got all 5 of those MATLAB files there. So if you're familiar with MATLAB, you have MATLAB license, great, go ahead and use this. Like I said, we're going to restructure this into Python so that we have an open source version so you don't have to worry about licensing or anything like that. And you can incorporate into anything that you are using. Excuse me. So just to kind of, in case you are interested in going in and either understanding what all the assumptions are, or modifying some of those assumptions, or just in general working through some of these pieces, I'm going to kind of walk through this a little bit and kind of give you a breakdown of what this looks like. So there's a big chunk of information here, which is all this first stuff, is all just text parsing. So we're going to kind of skip over this. This is literally like the first 2,000 lines or so. So I'm literally going to fold up some of this so we don't have to look at it. So still text parsing, still text parsing. Now we're starting to text write. Basically, this is just kind of getting some very basic information in there. Kicking off, do we need a battery schedule because we actually wanted to do a battery model. Things like that. Adding the correct climate files and things like that. Adding our substation transformer. But then what we really want to do is try to figure out. Sorry, we're not there yet. Notice here, this is one thing I didn't notice. We actually put a player file on our swing node, so we get voltages that are being played in. We pulled these voltages from, I think, from a WEC website that was a standard. Basically, that had a year-long set of data that we captured the voltage off of, converted back to sub-transmission voltage levels, in this case 230 kV, and use that as a player file to be representative of what the voltage variation might be at a location, at a substation. Note that's completely different depending on where you are and what who you're working with, but for our basic model, this is what we used. We did things like cleaned it up and made sure that there was no voltage dropouts and things like that, but effectively we're just playing in that. And the reason being is because we wanted to see some kind of standard regulator actions. If you put this, if you set these voltage at the swing node to just a flat voltage, then basically your regulators never move because all they're doing is regulating, for the most part, your variations in transmission voltage. So we're really trying to capture that behavior. So that's why we have these in here. So here's a little bit more text parsing, but I want to kind of stop at one spot here and kind of look at it here, kind of give you an idea what we're trying to look at. Brian, the Python scripts are not. We're working on those independently on another project, and when we're done with the project, we'll be able to put those out on the SourceForge account. So the piece I want to look at is when we're actually looking at, if I can kind of, here we go, where we're actually creating the house models or deciding how many house models to actually put on here. So you can see it's going through the script and it's finding values for either Power 1 or Power 1.2, which are the loads at the triplex level. And it's making a decision about how many houses we should put on there. You can see that it's basically taking the rounded value of the VA value at that location, dividing it by the average house size that we're looking at. That's coming out of taxonomy data. And then we do a little bit of skewing for what we call large and small homes. So the reason that we want to do that is depending on whether we round it up or round it down, we want to kind of skew the size of those homes in one direction or the other. And then we do things like describe the sizing of the center tap that we want to use for those houses. And then in a few cases, and I bring this one up because we've had questions about this one before, when the loads are too small, so a lot of the databases that we get will have things like 10-watt loads or 100-watt loads, which I'll call too small for creating a house to. We might do something like we'll convert those to streetlights. So there's we actually have a flag that you see in the, I think it's in the technology parameters section that says, well, what too small is too small, and at that point we just convert it to basically to a instead of putting nothing there, we convert it to a street light and just apply a very simple load behavior there. And the reason you see some of these 10 or 100-watt loads is, one, they may be actual loads. They could be something like a street light or a like a metered pump or something like that. But often what they are is they're artifacts of load allocation studies. So when you actually are allocating the load across the feeder from the peak load study, there's residuals that get left over and those get populated on there. Because this may be maybe there's a single meter way down on the feeder, and that's the residual that's left over from the algorithm. So it gets assigned a very small value. Rather than trying to figure out what each of those are, especially on these very broad models, we just assign it. Once you get, you can see here, less than average, 1/2 the average house size, we just assign streetlights to it. So if you start tweaking with some of the things like the average house size, and you make the average house size, say, very, very large, like 40,000 or 40 kVA, you might get a lot of quote-unquote street lighting that looks a little odd. That's all because it's designed to scale to the peak loads that we were looking at for the taxonomy feeders. So we get through all that. We're all done with the text parsing now. Then what I want to show you is the fact that when you get into the script, it's really broken down into a number of different sections. So this section here is basically, if we're using markets, what should we do? And you can see there's a bunch of information that gets populated, things like what's the market penetration level, how sensitive are people to the actual pricing, what is my randomized elasticity values, so we don't all get the same exact elasticity, things like this. Things like setting flags for solar. Really what I want to get to is actually how we populate the house here. So we get to this location here. This is all about how we are actually going to write the house in there. And this is a big, long section, so I kind of want to just scroll through it really, really quick to show you just how much goes into creating these houses. So we're still creating one house, still creating one house. There we go, we finished. So you can see a majority of the script is actually designed to create the house. But this is where we actually pull in the information from all these different external scripts that we've put together. So things like, what's the breakdown of our thermal integrities, i.e., 1960 versus 1950, and then how does that populate the rest of the information? So that when we actually come down here to create the triplex meter, we can look at the different billing types, set different skew values for different types of things. So for example, this is the skew value for the general house. This is the water heater skew value, and then this is the pool pump skew value. So they're slightly different, so you want to make sure to randomize those in a slightly different way. that you're capturing those different types of values. We go down, we actually create the, for example, we're grabbing from the floor area to actually decide what should the floor area be of this home. And then finally we get to the point where we actually start writing out the home. So things like floor area, stories, and that. Again, I'm not going to go into a lot of this. If you want to ask any individual questions, please do. I just kind of want to give you a general layout of where stuff is happening in this. Then you'll see things like here, again, we'll set the, we use the, if we want to use the market, then we're going to do something else. So in this case, we've created the HVAC system up here, but we said, oh, by the way, we're actually going to use a market. And what type of market will decide what type of controller we're going to put on this thing. So you can see, for example, here we've used the passive controller to actually to add direct load control to the HVAC system to say that we're going to do some forced cycling of the HVAC system. So we add that into this house model, and all the way through to kind of add these different things. If we're looking at, is it maybe we're doing a time of use or a real-time pricing type of scenario that might be in here. Different effects on our zip loads and things like that. So really, that's all this is really trying to do is it's creating this house with all the different possibilities that we could think of that we were going to do on these technology cases, but at the same time keeping all the other stuff exactly the same. So to get here past the houses, for example, then we do the exact same thing with the commercial buildings, which has a little bit different stuff, but basically the same idea. It's creating a house that has a bunch of different parameters set. So I'm going to skip over most of this because it's very similar. What I want to get to is the next piece here, is that once we're done creating all these houses and the street loads, or light loads, and that, there's other things that we have to create. So for example, here is where we start the actual battery creation. So if we wanted to do a battery model, we would add this battery on to say, okay, well, here's a centralized battery versus decentralized battery. So we had to capture the information about where could we actually populate decentralized batteries. So i.e., where are all the center tap transformers? And so what would the different names of all the center tap transformers be? So therefore, we could parent the battery to those different locations. And the one thing to note here is now we've moved on to, in this case, we're doing the solar study. So note we set this random stream number generator right here. The key to this is that this way that as we're moving through this script, we're not re-randomizing or changing any of the pieces that we did before would affect the things after. So if I change my parameters from up above and generated 10,000 houses instead of 5,000 houses, it doesn't matter. I'm still going to get the same random numbers in this section. So that when I populate the solar models, again, they are the same as what they will always be. If I change something in the solar area, the earlier area will always be the same. So you're not having any effect on your different sections. As long as you keep, as long as you're only changing one section, then that's the only area that's going to have different things coming out into the final GLM. So this is really doing a lot of things. Really, it's just trying to decide how many solar panels to populate in each location, depending on your penetration levels. Once it does that, it actually populates the new triplex meter, an inverter, a solar panel, and things like that, and determining what size to actually put onto it. In this case, you can see it's a hard-coded area, but you could actually adjust that area to whatever you'd like. It does the same thing with the commercial buildings and things like that. If we get past here, past solar, then we get to the next section. You can see we're doing, this is thermal storage. So we're populating thermal storage on a bunch of the commercial buildings. Again, same idea. We set a new random stream, and we're now populating it with the object thermal storage on the different commercial buildings. Same thing here. Now we're going to add a wind generator. Of course, there's no randomization in the wind generator, so because these are all standard sizing ones, we didn't have to do a new stream. Here we have another blocked out place that we don't actually use anymore. We started to create some emissions code, but we didn't actually end up using it. And then we get down to the bottom here, which is all kind of our collectors and tapes and things like that. So this was kind of, I just want to kind of give you a breakdown. Like I said, there's a lot here. I don't expect you to take a lot away from it, except that if you went back and wanted to make some modifications and use this for your own study, then you kind of know where stuff is, and you can kind of look at the different assumptions and make sure that you're happy with the assumptions, because they are assumptions in most cases. You know, each of these different studies has their own built-in assumptions, and you just have to be aware of what those might be and modify them if you need to. Let's see, so Tony, looks like you got a question about the maximum on here. We can look that up. So if we go to object solar, for example, here, there's not really a, what I'll call like a hard limit on there, but there is a limit that's built into, basically all the solar panels are sized as a function of the floor area. So for example, this is the residential solar arrays. You can see it takes the floor area, which is a, I'm trying to remember where this is actually coming from. So there's the solar residential array, which was set from, I'm trying to find it here. There we go. So total. So basically, it's saying, okay, you know, if we choose if we choose this house to have a solar panel, which is driven by the penetration level, then we're going to come down here and we're going to take a look at the floor area of that home, and we're going to say we want something between, I'm trying to remember what that is, in between 162 and 270 square meters, and choose that floor area that goes in between those two values. So and we're going to basically take 10% of the floor area to get that value. It's kind of a rough approximation to say that we're going to cover about 10% of the floor area with solar panels, and then we're going to chop it off with those two size restrictions. So each of those, whether it's commercial or residential, has some kind of assumption built in like that. I think the fact that commercials are just hard written to say we want like 5,000 square feet. So again, if that's a assumption you would like to change, then you would just need to go in there. For example, this is the strip malls, which are all very very simple buildings, which all have the same size. So you can see the floor area is just, or the surface area of the solar panel is just hard set to 538 square meters. I think that's square meters. It might be square feet. I can't remember off the top of my head here. But you can see that it's actually set to that value. Yeah, floor area is a little misleading there. That should probably be more like you know, surface square footage or something like that. So yeah, like I said, again, this was the assumption we made for our study. Feel free to change it. That's why we put these out there, and make your own kind of assumptions that would go into it. So there's just a couple little other things I want to hit on here, and then I'm going to completely open this up to questions for people. Or feel free to ask, you know, continue asking them now. A little kind of I guess as Frank put it, a user beware, or kind of a heads up on this a little bit. I will be completely honest right now that this calibration, load calibration study is a little bit of black magic. You know, I showed you kind of the big knob that we have right now, which is modifying the house VA, which is kind of the big knob that lets us turn it back and forth and kind of calibrate this this on the global, on a gross scale, what this looks like. It doesn't guarantee that your load shape is going to look exactly like the load shape you expect. It'll have the right, it may have the same peak, but it may be shifted off in time by 2 hours, or it may be more flat than what you're expecting from your data. So once we go beyond this point, that's where things become a little bit trickier. That's where it's a little bit of doing things like, okay, we're going to look at, maybe the percentage of load of HVAC is not quite as clear-cut as we thought from the survey data that we looked at. It's really going in and kind of looking at a comparison of these two load shapes and trying to understand what the differences might be. So, for example, if I have feeder data that looks like it's an afternoon peaking unit, and mine is showing something more like a morning peaking unit, what I may go back and do is actually record out the different end-use components to try to understand who's peaking in the morning and causing that peak, and then try to modify the load shape behavior so that it's more representative of the feeder I'm looking at. So again, this is kind of one of those things that right now this is a pretty, I'm going to call it very much a black magic art, a lot of user experience type of thing to really get it as good as you need it. I put good in quotes here. So we have been able to match load shapes across an entire year, again throwing out things like holidays or the Super Bowl or something like that. But we've been able to match loads within about 3 to 5% at any given time, usually on 15-minute measurement intervals, match it at the substation level. We've never zeroed in to look at, does an individual transformer look right? I will probably almost guarantee it doesn't. But that takes a fair amount of effort and a little bit of know-how and a little bit of understanding what's going on in the system to kind of get to that point. Things like these prototypical feeders, of course, we didn't have shapes to match to, so that was no big deal. We didn't have anything to match. All we had to do was match with the peak. So I guess what I'm getting at is just be aware that this is not necessarily a super easy process, and right now it's very much a human-in-the-loop process. We're working on a project right now that's looking at trying to automate those in some kind of fashion. I believe we're going to be able to make that open source and openly available to anyone. I'm not positive about that right now. Because right now this is very much for us even a hardware in the loop piece of it. Let's see. Frank, you're looking for a link. There's one on the right on the SourceForge wiki. If you go to right on the very main page, there's a link that says related reports, and they're in there. So yeah, so just kind of a warning there. It's these MATLAB scripts are of what we've done to automate the process, at least as far as generating the models themselves. And typically what we'll do is we won't run a whole year when we're trying to do this calibration. We'll pick maybe 3 to a half dozen days that are what we'll consider to be representative, say like a peak summer day, maybe an off-shoulder day, and a peak winter day, and then maybe just kind of an average summer day or something like that. And we'll try to match those 4 days really, really well. We'll spend some time, modifying the load shapes a little bit, modifying the house VA value, penetration levels, things like that, until we're happy with those days, and that becomes our settings. And then we run the feeder for the annual simulation if that's what we're looking for, or month, or whatever that might be. We don't run the whole year and try to match that from the very get-go. We usually only do about 2 or 3 days that we really match really, really tightly. Get those down to to an acceptable level, 1 to 2% difference in that range, sometimes larger depending on what we're trying to do. And then the other days we just kind of let those fall out however they might be. So one other thing I want to talk about really quick about this is weather data. So TMY data is everyone's probably aware, is very, very average data. It's stitched together data from a number of resources that It's trying to represent what the average year looks like. That does not match the weather that goes along with, say, substation SCADA data. So if you're trying to do any type of calibration where you're looking at the feeder real and reactive power or voltage or whatever that might be, you're going to need to match that to the weather at that substation on those days. So if you're looking at an annual simulation to do calibration, annual or daily, that weather needs to be pulled from some kind of weather source, not from TMY data. I bring this up because I've seen this a couple times where folks couldn't match their shapes to what was going on the feeders on those days, but they were using TMY data. And that's because, you know, August 4th on TMY could be, you know, could be 65 degrees, but on that actual day, it could have been 100 degrees. So those are since they're so correlated, you most definitely need to update your weather model before you start doing your calibration. So, for example, the way we've done it many times, and I think I talked a little about this in the climate module, is the big ones that we want to capture on there are temperature, humidity, and some kind of solar instance. These can sometimes require a fair amount of data processing to get to that point. My favorite resource is Weather Underground, actually, because they actually record that data over the course of years. And I think they have data all the way back to about 2006, 2007, and they display it on an HTML format that's pretty easy to parse and things like that. But again, that information needs to be timestamp matched with your SCADA substation data or whatever you're using to calibrate your load to. Because if you don't, then you're going to get some serious differences in there. One thing to be aware of is when you're converting this over, and we use what we call the CSV reader to process that, be aware of any large step changes in data. So we do a little bit, when we capture that data from say an airport, occasionally they'll have like a data outage or something like that. You want to make sure to interpolate across those areas so that you don't have any large step changes in the information. Because it's basically the ETP model, that's the thermal model that's driven, that is the house and other pieces of there in there. They're basically a second order differential equation. So it's basically like if you take the temperature and do a 10-degree step change, you're basically stimulating a second order differential equation, and you get some odd oscillations. So you just want to make sure if you're capturing any type of that data, do some interpolation, do some smoothing on it, so that you're not getting any kind of weird things happening on there. I'll show you an example of that. I specifically picked this one just to show it. You can see this little swing right here, not this bottom one, but this one right here. That little swing in the load is because there was a bad piece of data. Actually, it's this whole section right here. There's some bad data in the weather file, and when we did the interpolation, it interpolated this piece low, and so you get this kind of weird dip in the load shape that really probably didn't happen in an actual feeder because the temperature didn't actually drop by 5 or 6 degrees in a 30-minute window. So you can see that there's kind of a little bit of an oddity there. And that was actually caused by the fact that the weather that we were using had some odd data in it. So that's really, that's all the prepared material that I have for today. Really what I want to do is kind of open up to questions and see what people are interested in hearing about, or try to answer any questions that folks might have, either about this process or even opinions about a process maybe you're working on that you want some advice on. I'll say we don't have all the answers. We've worked with a lot of other folks that are trying to find better answers. We're also trying to work on an automated method for this, kind of an engineer out of the loop type of approach that hopefully we can, like I said, hopefully we can release to the public at the end of the summer, but I have no guarantee on that at this point. That doesn't mean all the knowledge isn't locked inside the head here. So any questions, thoughts, concerns, fear factors?
This is Bob O'Hagan. Can you hear me?
Yes, Bob.
Okay. We've been doing a lot of work on converting a multi-speak file over, and we've got some stated data. So if I can get you to go back to your slide 22 about creating loads. And where you got the P and the Q.
Yes.
There. And do you recommend just doing separate P and Q, or should we go with S, you know, the R theta kind of format with S and the angle?
Yeah, so it would depend on, you know, how you're going to ultimately put it in there. So most of our load objects that we have in GridLab can accept it in either format because it will accept a complex number. So it can either be in, you know, R plus you know, some kind of J value, or it can be the plus, you know, 31 degrees or whatever it might be.
Right.
So either one's acceptable. The key to that though is if you're going to break it out into separate player values. So like I have it right here. So in this case, it is a single player that we're applying to both of these. But there's cases where you may want to have a different player for each of these. We only typically break those loads up to access the different components in rectangular coordinates, not in angular coordinates.
Okay.
That would be the only catch on there, though, I would say.
So if we wanted to simulate some voltage regulating activity with reactive power or something like that.
Yeah, it might be important to separate them out that way then.
Okay. Also, can you force the reporting to be either format?
I don't believe so.
Which is
yeah. So you're
pretty
trying
much
to pull
real
it
and reactive.
So are you trying to pull it out of the XML or out of the player files? Or report files, excuse me.
Yeah, the report files, the recorders.
Other recorders. So yeah, you can't force the format there, but what you can do is you can record the individual components. So you can have it record .real, .imaginary, or .magnitude and .arg, I think it is, angle. Maybe it's .ang, I can't remember which one it is.
Okay, so you can do the dot angle. Okay.
Yeah, so you can, it comes out as two different columns that way. So you have to parse them back together, but so you can extract the information that way.
Okay, and we don't have to worry about the positive sequence 120-degree offsets, right, between phases. You take care of that. We just give you power factors or relative angles. Correct.
Yes. So yeah. So as long as the swing node is set with, you know, your 120-degree shifts, then all the rest gets solved. But then when you're looking at your load behavior, if you're using constant power or constant impedance type of loads, they automatically adjust. And I want to put a little caveat on that. It's because the constant current ones, constant current's a little weird because it's got to have an angle to be offset against. So as long as you're posting that as constant current or constant impedance, yes, you don't have to worry about an angle at all. It will just take care of it for you.
Constant power or constant impedance.
Yeah, yeah. Sorry, I'm sorry. Yes.
Right. Yeah, we're not messing with the load. I mean, with the currents.
Okay. Kind of a secondary caveat on that. Oh. Well, I just wanted to point out that I can't remember if it's in 2.2, 2.3, or which version we put it in, but there was something added to the load objects where you could specify it kind of like the IEEE taxonomy or the prototypical feeders, where you specify just kind of the power of the constant current load and then give it the power factor, and inside GridLab it'll handle all the angle offsets. It's only if you're using like the constant current underscore A underscore B underscore C that you have to worry about the angle offset. If you do it the other way, it's meant so you don't have to worry about that angle offset. So it depends on how you're playing it into your load, basically.
Okay. And you know, is there a good example of setting the swing node positive sequence? values. I haven't been working on that part directly, and Cedric, who normally has been, couldn't make the call today, so I just want to make sure that.
Yeah, so if you just set your swing node to a nominal voltage, so you don't explicitly declare voltage A, voltage B, and voltage C, it will take it and say that voltage A has a 0 angle, voltage B has plus 120.
Okay, you do that internally. Okay,
yep,
so we just set the nominal voltage, and okay.
Yep.
So for us, it's a do nothing but the normal.
Exactly, exactly.
You did it the way we wished you'd done it.
I don't think that was originally that way either. So I think someone came back and said, you know, this is really kind of dumb, guys. You should try doing it this way.
Yeah, because we were having trouble interpreting some outputs we were getting, and we got different direction currents on phase A versus B and C, and I wanted to make sure that there was nothing else we were doing driving it.
Right.
Directly to cause those. So now we can debug why the current direction of some nodes is weird.
Something to point out really quick on the whole kind of sequence conversion thing. As Jason mentioned, you can set it with the nominal voltage and it'll automatically populate the plus minus 120. The caveat on that is it only does it for the very first one. So if you were trying to do what we were doing in these studies with like a player driving that, after that first step, the nominal voltage won't be adjusted automatically like that anymore. You have to play it into the individual A, B, and C phase. It's only on the initialization that it'll take that nominal voltage value and automatically populate the 0, 120, and minus 120. So if you want to get the subtransmission effects, you do still have to put those in directly as the voltage A, voltage B, voltage C.
Okay, with the offsets included?
Yes, with the offsets included. If you wanted that time varying voltage like we did for the population script that Jason just went over. If you just wanted it to be a fixed value, then you just have to put it into that nominal voltage once. Essentially, if you do a player on a nominal voltage, go ahead.
Yeah, so if we're just assuming we've got the nominal voltage coming into the substation, then we don't need a player file there, and then we can just put all our loads and solar sources out on the feeders and watch what happens, right?
Yeah, in that case, you just have to set the nominal voltage once, and then it'll automatically handle the angle offsets for the phase B and C for you.
Okay. If we start getting that fancy, we'll get back to you. Would you normally do that to be looking for some kind of transient effects?
Yeah, usually we include those players because we want to look at what the capacitors and regulators are doing on the system.
Okay.
Typically,
so that's it.
Yeah, go ahead.
That's how you drive the regulators.
Exactly.
We've been having trouble getting enough voltage swing to make the regulators do anything.
Right, because those are typically there to kind of adjust for your transmission level voltage variations.
Right.
Not necessarily for feeder voltage variation levels.
Right.
Yeah, something we ran into a few years ago where we were scratching our head. It's like, why can't we get any regulator action? What's going on here? It's like, oh, the light bulb went off. And
oh, it's on the source side, not the.
Yeah, exactly.
There is.
The one case, the one caveat to that case is if it's any kind of line drop compensation methodology. So if they use like an LDC, then you can see some action without varying the source voltage.
And what would be the best way to induce some of those somewhat artificially? We want to make sure it works. I mean, should we go to longer line lengths and skinnier wires or something to induce more voltage drops? Or
yeah, you're trying to get you need a feeder that's got more problems than it actually does. I guess is probably the best way.
Yeah, we want to induce problems and then show how some of the smart grid techniques can fix them.
Yeah, yeah. Basically, what you want to do is somehow increase the impedance across, especially the trunk lines themselves. If you can get those main primary lines with increased impedance, then yeah, that'll very quickly show you some large voltage drops.
Okay. We'll try putting some speaker wire in there and see what,
exactly.
what happens. Okay, thanks.
Yeah, no problem. Any other questions?
I I've got one other.
Oh, keep going.
I'm the only one. Yeah, I can't believe I'm the only one talking today. And just to confirm, with going off our SCADA data, the algebraic sign that's associated with the Q between, you know, what we recorded on the SCADA data source, we still, you know, if it's normal negative there, then the load should be also negative. On the,
correct, yeah.
Yeah, the power factor interpretation. Right?
Yep, exactly, yeah.
Yeah.
Yeah, it's I'll be quite honest. You know, I think of it leading, lagging, so positive, negative gets me confused sometimes. So I always have to walk back through it a couple times to make sure I'm getting it right.
Inductive, capacitive, yeah.
Yeah, exactly. So.
And then I see the charts in the EPI report that show the difference between IEEE and IEC. And
yeah, exactly. Well, I think Frank's comment in the text there was about right. Unless it looks wrong, then reverse it. You know.
Yeah.
Yeah, I think there's just so many different standards for what that, you know, especially, you know, when you start looking at, well, if you're looking at it from SCADA data, what is that? Is that the stuff being injected into the transmission side or drawn from the transmission side? Then your sign is, you know, could be reversed and things like that. So we tried to make it as close to standard notation as we could, and that being that we're treating it as flowing down from the substation, so your load would be pushing that back up.
And your lagging should have a negative power factor, right?
Yep, exactly.
Okay, that's the way we've been interpreting it.
Okay.
You know, our bigger problem in our model was too many errors. It was obvious our model, it was windmill output as multi-speak. And it became very obvious that it did have data down to the service location, to the meter level.
Yeah, windmill's really good about that.
But it was obvious they had never run the model because there were too many errors where along a bunch of wires they would switch phases and things like that.
Oh, right, right. I have seen that
so
before.
We finally, you know, different people entering data at different times, and we finally just had the right scripts to trim all the meters off.
Oh, that's unfortunate.
And go at the transformer level.
Right, right.
But your scaling factor, your MX plus B approach works quite well for us. So.
Good, good. I'm glad to hear that. Well, any other further questions? You know, it doesn't have to be limited to this subject area right here. You know, we can go back to some of the other questions that might have come up in other classes or you know, other things. So, you know, feel free to pick Frank's in my brain while we're here.
Okay, I got another one for you.
Okay.
I hate being the only one at the front of the room waving my hand. We're also looking for a flicker. Is there a percent change that you consider to be noticeable?
So that's a good question. The only official stuff that I know of came out of GE probably about 15, 20 years ago. They created a flicker chart, and I have a copy of it somewhere. I can dig it up. But basically it kind of says it's a combination of how deep the voltage drop is and then how often it occurs. It's not a single, you know, it's not a single value. And so they designed a curve that was basically, they interviewed, you know, hundreds or thousands of people and said, well, here's this curve that kind of defines how fast and how deep equals flicker, where people can notice. Well, if I can dig that up, I can send it to you.
Okay, I'll send you an email.
Yeah.
And obviously this type of simulation isn't going to show it directly, but what we're hoping is that, you know, we're trying to do stuff at 1 minute levels, and if we can see some kind of significant difference, you know, we're trying to yank our solar full on, full off at noon, things like that, and see what type of variations. And, you know, most grids are robust enough. They're not going to show severe problems there, assuming you've got the nominal voltage coming into the substation. but we would like to imply where there might have been flicker in cases like that.
Yeah, absolutely. Yeah, I mean that's one of the big concerns with solar right now, right? Is that they're worried on a weak system you might see some voltage flicker, and whether that happens.
Well, but that's the other thing. If we can get active inverters participating in local voltage regulation, it should cut down on that.
Right, exactly.
Pretty dramatically.
Yeah, yeah. Yeah, because now, especially if you're using your 4-quadrant control rather than just real power output, you can affect voltage a lot quicker and a lot easier with your reactive power than you can with your real power.
Yeah, if you've got energy storage, you got a lot of options. But even with just the 2-quadrant off solar, if you can combine it with some forecasting, to do some ramping down,
Yep. Yep, absolutely.
One error message we were getting as we were trying to break things was emergency ratings on overhead lines. And do you know where that comes from?
So it's probably saying something like line something is 120% over limit or something like that. Throwing out
I think I would have to go back and dig up an email here.
So that was a warning that we added somewhere near the end of version 2.2, I think, maybe 2.3. It is just a warning. It doesn't actually cause the model to fail, but if it becomes annoying, you can add a global value to turn them off. Let me I'll pull it up on the screen here. So.
My screen stopped a while ago.
Oh, still
link problems.
So yeah. Oh, there. Frank just put it into the message thing. So if you add it into module power flow, so it looks something like module power flow like this, and then.
Oh, it's not even updating that for me.
Oh, really? Okay. So it's there.
It was intermittent. It was dropping in and out, but it would usually let me rejoin. And now I've got other, internet services running.
Oh, I apologize about that.
Oh, well, it just says sharing ended due to network issues.
So yeah, so if you do in your module power flow setting, if you put line limits space false, it will turn off all those warnings for you.
Is it line underscore?
Yep, line underscore limits space false. Yeah, Tony, it still shows all your errors and fatal messages. All it does is just turns off that particular warning that says, you're 150% over your rated limit or 105% over your rated limit. Because obviously, a lot of these are heat-driven, not current-driven, so.
There's not a parameter on our wires we need to look at.
You can. So it's there's a setting on every single line object that you can do. I think it's summer continuous dot emergency rating.
Okay.
That is basically it's how much the it's on the conductors, not on the lines themselves. That says basically what's the emergency limit of those values. And really, it's there for us. It's for when we're doing some kind of short circuit or reliability studies or things like that. As far as the base model goes, it doesn't actually do anything. It's a good indicator to tell you, maybe you've got your loads configured wrong. Like if you see a line that says I'm at 800% of my rated limit, it's a good indicator to go, oh well, let's go check that load. Oh yeah, I did add an extra 0. My bad.
Yeah, well, I mean, we're intentionally putting little, 0.5-megawatt solar farms at spots along the feeders, so we know we're going to be
exactly. So yeah,
we're trying to blow things up and make sure that the protection is working and things like that. But.
Right. And so, if you just add that flag into your module power flow, it'll actually turn all those warnings off, so you don't have to see them.
Okay.
So I saw, Tony, did that kind of answer your questions about the XMLs, or was there more to it there? Okay, perfect.
Another question on power and loads, is the default unit of measure always kVA?
No, not necessarily. In fact, in the PowerFlow module, it's almost always VA. When you move over to residential, it's almost always kVA, or actually kW, because it was by who was written by. So for power engineers, at least the way we were doing it, we were thinking of it in terms of watts and volts, while the residential engineers, they all think of things in kilowatts. So relying on a certain default unit is not necessarily a good idea, but any time that you want to use a certain units, just put them in there. So if you want to list it in kVA instead of VA, just put the unit kVA at the end.
Okay, we can put that in our player file.
So that was going to be the one exception, not in player files. So in player files, it's relying on you to take care of the unit conversions correctly.
Okay, so player files, we should assume VA for power?
So this is in the PowerFlow module?
Yeah, in the PowerFlow module.
Then yes, yeah. All of them in PowerFlow are VAs.
Okay.
And you can always check units to see if if you're using a new variable that you've never used before. You can use the mod help function out of the command line that will let you check the units.
Oh, okay. I remember that's just -H or -help.
So it's so you type in GridLAB-D -- mod help, and then the module that you're interested in, colon, the objects you're interested in. So, for example, for load, it would be PowerFlow : load. And that will print out all the different parameters that are in the actually in the load object and what their units are. And even a brief description of them.
Perfect. And will we see a significant error or loss of accuracy applying our loads to the transformers instead of to the meters, as it reflects?
Oh,
from the feeders.
Yeah, so you're applying at the secondary side of the transformer? Or,
we'd like to.
Yeah. Most of the runs of triplex cabling are, in the order of like 10 to 50 feet. You might get a volt drop across them. The standard utility idea is across the transformer, the cable, and the meter itself, you have about a 3-volt drop. So, it's not.
Yeah.
Not having that in there is not the end of the world.
Okay.
Triplex cabling hasn't been in those models for 50 years, so.
On a totally different question, this is Brian Pomtier. I'm looking ahead at the sort of possible upcoming training schedules, and it looks undecided. Is there any input or any insight into what might be coming up down the pipe for this series?
Yes, yeah, actually, thank you for reminding me. So next month we were supposed to have a developers training course, which we're going to have to unfortunately delay. David Chaston, who was actually the original creator of GridLab, was going to teach the class, but because of some other schedule rearrangements and the fact that he decided to go back to school this summer, he's kind of unloading a lot of his workload right now and isn't going to be able to do that. He is going to do it in August when he gets back, though. So we're going to delay that by about 3 or 4 months. But besides that, those are the ones that we've already given, and in that class, we don't have anything else in the schedule. And the reason was that's all of the prepared material that we have. I was hoping that people would give some feedback about, oh, we'd really like to spend some more time on this. Can you develop a class for this? And if we can get some of that information back, then we'd love to. We'd sit down and I'd write a new class out, and it might be a pretty informal one, maybe only an hour or so or something like that, but depending on the subject area. But if people have ideas, I'm perfectly happy to do another one. we could even just do standing monthly open calls. If people have that idea that they just want to get on the phone and spend an hour just kind of hashing out new ideas, perfectly willing to do that. But the reason they're all to be determined is because we're out of ideas of what to teach. Quite honestly, we don't have 12. We don't have 12 modules. We only have about 7. So
that sounds good. One thing I haven't dug into, I haven't been able to attend or see all the material in the past ones, but the use of GridLAB-D for sort of beyond the time series analysis, some of the more protection coordination and some of the other sort of faster dynamic stuff would be interesting to hear some insights into.
Yeah, that would be good, especially when you get done writing the code that does that. I joke because we don't actually really do much of that. We have very, very limited of those components. And the whole reason that we were trying to stay away from it is because there's tools like Windmill and Simon Synergy that do that extremely well. And we're trying to push out into the areas that these tools don't really capture, which is the time series aspect.
Yep.
So we've been very careful about not competing with those guys. Actually, we work quite a bit. So that's one area that we have specifically not done development in.
Okay. People have been doing some work in that area, though. Is that right? Or has that not been stuff you've done, or is that?
We've done some very limited work. So we put in the basic short circuit capabilities. We put in some basic other components that go along with that. But they're more in there kind of stubbed in so that people can look at it and say, oh, okay, here's where I would insert my stuff if I was going to do that. Really the idea is, the great thing would be is if a commercial vendor came along and took it and said, oh, yeah, all this is missing. Let's put in short circuit or whatever that might be.
Yep.
That said, the one piece we have been working on is what we're calling Delta mode, which is the very first pieces of it came out in 2.3, but we're really going to start coming out in 3.0 and 3.1. And they're really designed to look at sub-second dynamics, so sub-second machine dynamics specifically for unbalanced systems. So that's where we're trying to get to that transient level of behavior.
Yep.
So those pieces will be filtering in the next probably year or so, year and a half maybe.
Great, thanks.
Yeah, not a problem.
Okay, so that transient behavior would let us look at undershoot and overshoot then from line faults to clear and things like that?
Ideally, yes. So our goal right now, and Frank maybe can talk a little bit more about this because he's the one who's actually leading the development on it. Frank, are you still on the line there?
Yeah, I'm still here. I'm trying to look up Tony's question right now.
Oh, okay. I don't know if you caught the question there. It's kind of what capabilities are we going to try to capture in the microgrid delta mode type of stuff? And are we going to be looking at fault dynamics and things like that?
I'm not sure if we're going to make it into that. The goal for this year is we're trying to add in some of kind of like the line charging and transformer charging type dynamics. And then, so if you're doing restoration type work, that's what we're looking at. And the other one is getting kind of some more detailed dynamic level models, transient level stability for inverters. So if you wanted to do like rapid cloud transients or something like that, we could look into that. I don't know if we're really going to get in anything specific to fault type scenarios. I know we won't get to coordinated protection schemes or anything like that, as Jason mentioned, but we might get some simplistic fault inclusion. The other thing I would like to do, but I don't know if we'll fit it into our timelines and our funding, is right now, like the reliability module will give you a variation on the IEEE, or a version of the IEEE 1366 metrics. Of course, it's built off of the old GridLAB-D framework where you're doing 1 second or larger time steps, so some of the things like recloser actions you don't quite capture right. I'd like to at least get the quote-unquote delta mode or the transient functionality into reliability, so in the future we could expand that, or if somebody in the community wanted to, it would be allowed, but I don't know if we're going to get to that this year or not. Most of it's going to be primarily focused on kind of the inverter dynamics and then the restoration type work, mainly towards like microgrid scenarios.
Within that, is there some work on the sort of anti-islanding as well, or?
I don't know if we'll get that far into detail this year. I'm not 100% sure yet. We're still kind of scoping out the work.
Okay.
Okay, so right now you don't have anything. This is Bob O'Hagan. You don't have anything that will simulate the IEEE, 1547 must clear type requirements.
No,
not at this time.
Yeah, because if you're looking at it from a very broad perspective, because it's like a six-tenths of a second, and then there's the 3-second clearing, I think it is. So yes, you could represent the 3-second clearing, but it would be a little kludged, quite honestly, because you wouldn't actually be doing the point on wave or trying to understand, did I actually detect it correctly? But you could actually tell it to say, oh, if something happens, then drop out in 3 seconds. And you could capture that type of effect.
So we've got low voltage ride-through by default right now.
A little bit, yeah. Yeah, no, certainly the inverter models that we wrote in there are very, very generic. We didn't want to put a lot of those specific rules in there. But you could very easily go in there and write a rule inside the inverter model that would be, if voltage is under this level for 3 seconds, then we actually have an in-service and out-of-service flag, so you could knock it out of service and things like that. It would not take much to add that in there, so probably even as an external code extension through the runtime classes.
Yeah. Okay, thanks.
Yep. I think I think both Frank and I are checking this line limits thing, make sure we set it right. So, but if there's other questions.
I've got one about converting data from other formats.
Yes.
Most of the other formats use, like what we discovered with multi-speak. It just had the simple link element. It didn't have the separate nodes. So we had to do some finagling. We used MapForce as our conversion tool. But, we had to sort of artificially create the nodes connecting the link objects.
Right, so I'm not super familiar with multi-speak, so I can't talk too much about that. But, yes, we've always had to do some kind of little trickery like that in there. If you would, those Python or the Perl scripts that we have available on there, if you take a look at those, there's places where we've done that exact thing. We looked at it and said, wait a minute, these two nodes, these are actually the same node when you look at it from a topological point of view. But, for whatever reason, these models have it connected by, a zero-length connector or something like that. So we try to do some of those in that conversion process to try to reduce it to topologically what makes sense.
Yeah, and we just use naming conventions to match, say, an upstream node to its link object, and then the parent relationship to connect the downstream.
Exactly.
Link an object to the upstream.
Yeah, no, you're exactly right. Trying to get those to line up can be a little bit of a pain sometimes. I would hope with multi-speak, especially since it's a little bit more rigid in its format as far as how you declare those different objects and things like that, that it would actually, once you have it done once, you would never have to worry about it again. But I'm not sure if that's true.
Yeah, this was our first experience with it, so we don't know. Again, it was a multi-speak output from windmill files, so we don't know what was lost, added, or changed in the translation.
Yep, exactly. And luckily those two are pretty tight at the hip, multi-speak and windmill. So, so ideally, whatever one utility is doing, they're between those two, because they're so tied together and they work across such a large utility base, they're a lot more, it's a lot more the same across utilities than it is for, say, Cyme or Synergy, where they do a lot of customization for each location. and depending on which database you pull in. So that's been my experience, at least. I don't know if that's actually true, but that's just my experience.
So just to kind of follow up, it was line limits, not line limit. I may have misspoke earlier. I don't know if everybody is able to receive the chat. I've been getting a lot of messages bounce back that certain people can't receive it. So I don't know if it's just certain people aren't in the chat or if the whole thing's failing out on me.
Well, that link connection stopped the chat box from scrolling.
Yeah, it seems like quite a few people might be having some problems with it this morning, so I apologize. But I'm obviously apologizing to the wrong people because you can all see. That may have been on our end. We may have had some service connection issues.
Did you say it was limit singular or limits plural?
Plural.
Plural, okay.
Yeah, I may not have had the S on the original one, so that's why I think Tony was encountering problems. Is I probably said the wrong thing, or we just mistyped it.
Perfect. Thanks for confirming, Tony. Appreciate it. Okay. Any other questions? Any other follow-up on this? Or, again, if folks have ideas about other subject areas they'd like to hear about, don't be afraid to send an email and let us know, and we'll see what we can do about putting together some more information. We quite honestly have a fairly large, how should I say, personal repositories of sample models and slides and things like that. That if we had a directed thing that we wanted to look at, we could certainly put together and provide another class for this. But otherwise, we're going to kind of start wrapping up for this year, and then start the classes up again next year. Hopefully, no one here would need them again, but if you do, they'll be available. And of course, we're going to post this one out to the website again within a day or two here, and people have access to it.
Okay, yeah, make sure they add the link on the SourceForge page over to today's class.
Yep, absolutely.
Well, thank you, guys.
Okay, well, I guess, yeah, if there's no questions, not a problem. I appreciate it. I appreciate everybody taking time to spend some time with us. And if there are any other questions, forums are always available, or if it's something a little bit more private that you want to cover up, then feel free to use email. But fastest response will definitely be via the forums because there's more of us monitoring it at any given time, so we can get back to you pretty quickly. Otherwise, thank you and have a good afternoon.